mostly neutron stars, um, as was just said, but I'm also going to try and talk a little bit more broadly about quantum fluids in astrophysics generally. And hopefully, I'll have time at the end to touch on a few other topics that are related, which many of you in the audience might already be quite familiar with. But I just want to sort of make the broad argument that quantum fluids are extremely relevant, not just sort of to terrestrial lab experiments, but also to many, many systems in space. Okay, so let me see if, okay. So I was already introduced, but I just want to give a little bit more context and explain my background. So as we just said, I'm currently at Caltech. I just started there as a postdoc. Um, and at the very start of my career in Australia, I worked with Professor Andrew Malatos, who many of you may know, at the University of Melbourne, studying essentially the superfluid interior of neutron stars using like Gross-Patevsky simulations and studying the vortex dynamics. And we were particularly interested in kind of the astrophysical observables that you can sort of see from the theoretical model of like quantum fluids, right? So more recently, for like the past 5 years, I've actually moved away from neutron stars and I've been studying binary black hole systems using perturbation theory. Um, so, once again, sort of focusing on like theoretical fundamental questions like the two-body problem and general relativity, and thinking about kind of the corresponding astrophysical observables, which in that case would be gravitational wave signals. So broadly speaking, I'm like a theoretical astrophysics with an interest in compact objects and gravitational waves. I'm definitely not an expert in quantum fluids like you all are. So please, bear with me if there's anything which, is outside of the scope of my expertise. But essentially, I want to sort of give you this talk from the perspective of an astrophysicist who is very interested in quantum fluids. And moving forward, I want to work on many topics related to quantum fluids in astrophysics, not just necessarily related to neutron stars, although these are probably one of the most interesting cases of this. So yeah, that's my pitch. That's what I'm hoping to convince you today, although I'm sure many of you don't need convincing. Okay, let's see. All right, yeah. So as I just said, this will be about quantum fluids in space. And we'll be focused mostly on neutron stars and their interior today, because that's a topic that I've worked on previously with several collaborators. I'm also going to briefly touch on at the end how quantum fluids relate to potentially dark matter in the form of like boson clouds and boson stars and things like this. And then I might briefly touch on how we can use like giant quantum vortices as analogs for black hole spacetimes, very briefly at the end. Okay, so now let's focus on neutron stars. Okay. All right. So I'm sure you all know what neutron stars are, but just to sort of set the scene a little bit, they're of course some of the densest objects in the universe. They're these, collapsed end states of stars. They're, essentially have like nuclear saturation density in their cores and higher. And they're, something like 1.4 times the mass of the sun compressed into like a 10-kilometer radius. They also have extremely strong magnetic fields. So you can see like orders of magnitude higher than the sun and very fast rotation. Um, again, many orders of magnitude faster than our sun. And this is obviously because they collapse and sort of through conservation of angular momentum flux and magnetic flux, they sort of end up with these very extreme rotations and magnetic fields. Okay, so this is kind of a schematic of a neutron star. So you have like some form of radiation, which is emitted in like a beam. And so as this sweeps across the Earth, we can measure their rotation very well. And that's really one of the key ways that we learn about their properties. Okay. So now I'm going to focus almost completely on the relationship between neutron stars and low temperature physics, right? So here we have something like a QCD phase diagram, and we have temperature and density. I'm not going to go through this diagram. I just wanted to point out sort of where the neutron star sits here. So neutron stars are obviously high density objects, as I just mentioned, but they're also low temperature in a specific sense, which is really what I think the interest of this community would be. And this is sort of directly complementary to things like particle collider experiments on the Earth, which are obviously very low density and high temperature. Okay. So there's sort of different lenses that you can use to study neutron stars. You can sort of focus on the sort of nuclear physics and studying bulk nuclear matter, which is, obviously very interesting. Um, and you can also exploit connections to low temperature experiments in theory. Um, and in particular, um, we can sort of exploit our knowledge of laboratory condensates to make progress in understanding neutron star physics, which many people have done for decades now. Okay. So just to sort of make it clear, what is exactly meant by cold or low temperature in this context. Of course, it just means that the neutron star is colder than sort of the critical temperature of superfluidity, right? So here we have a plot showing the critical temperatures at different parts of the neutron star's sort of interior. So here is sort of the crust of the neutron star. And obviously, as you go deeper, it gets more and more dense. So you sort of have different superfluids which emerge in different parts. So you have a triplet, which is the red kind of P wave superfluid, and you also have like an S wave, which is this blue, which is in the core. And just spoiler alert, we're really going to completely focus on the singlet superfluid here, and we're going to focus on really the outer core. But yeah, that'll come in a second. Okay, so hopefully you're all happy with this kind of picture of a neutron star. There are obviously many more complicated things going on, but we're going to just zoom in and focus on sort of the existence of this neutron superfluid in a neutron star and sort of exploit some connections with terrestrial low temperature physics. Okay. So the other point I want to make is as probably many of you know, neutron stars are not just neutrons. They're mostly neutrons, but they also have an electron and proton fluid. So if you start in kind of the outer crust, you have like this ionic nuclear lattice with an electron fluid. As you go deeper into the neutron star, the neutrons begin to drip out of the nuclei, and you end up with like this neutron superfluid, which I was just showing on the previous slide, which is likely to be like a P wave. As you go deeper into the core, you have, a complete fluid. Everything is fluid. It's going to be electrons, protons, and neutrons. And crucially, it is not just the neutrons that are superfluid. You also have a proton superconductor. And that's going to be something which I emphasize in the results that I talk about momentarily. As you go even deeper, you sort of enter this very unknown regime, I would say, which is, potentially like a quark-gluon plasma, like very high densities, which are sort of at the boundary of our understanding theoretically. And if you actually go back to that sort of phase diagram we had here, we're talking like this sort of high density, high temperature quark-gluon plasma regime out here. So that is very much beyond the scope of this talk. Oops. So that's a neutron star. And I think really the key takeaway that I want you to remember is in a neutron star, there exists a neutron superfluid and a proton superconductor, at least in kind of the outer core part of the neutron star. And that's going to really be the focus here. Okay. So you all work on quantum fluids. You know that, of course, if you have a rotating superfluid, um, you can develop quantum vortices, which in this case are about like 10 femtometers in size. Um, in addition, the superconductor is type 2 in at least in certain parts of the neutron star. And so you'll have flux tubes. Okay. So you can sort of imagine that this neutron star is something like, at least, as a toy model, a very simplistic picture, it's something like a rigid spherical container, like a bucket that is filled with this superfluid of neutrons and a superconductor of protons. And each of these fluids are threaded by their kind of respective quantum vortices. Okay. All right. So now I'm going to discuss how we can actually learn about quantum vortices through astrophysical observation. So I pointed out that the neutron star, as it spins, it sort of has a beam of radiation which can sweep across the Earth like a lighthouse, and this is how we kind of measure the rotation of the neutron star. So an isolated neutron star will just tend to spin down over time as it radiates and loses angular momentum, right? So you have this kind of steady stellar spin down. But this can be interrupted by these spasmodic spin up events called pulsar glitches, which I think many people in the audience are quite familiar with. But just in case you haven't seen this before, here's like an example of glitches in the Vela pulsar, for example. Also, Crab is another famous pulsar which exhibits glitches, although these glitches are slightly different to the ones in Vela. But at least one mechanism which we believe can cause pulsar glitches is vortex pinning in the neutron star. So essentially, the quantum vortices can pin to certain sites. So these could be sites in the nuclear lattice in the crust, or they could be to flux tubes. Um, and at some point, there's going to be like enough differential rotation between the crust and the superfluid that there's enough force to kind of unpin them. And when many vortices unpin simultaneously, it's expected that they can transfer angular momentum to the crust, and you have these like spasmodic spin-up events. So this is one possible mechanism for these pulsar glitches that we observe. So in this way, you can kind of connect astrophysical observables to like superfluid vortex dynamics inside of a neutron star, which is very interesting. Okay, but it can be quite challenging to actually connect these two things in, a sort of self-consistent quantitative way. Okay, so in my work with Professor Andrew Mlatos at the University of Melbourne, what we did is use Gross-Pitevsky simulations to study this vortex dynamics. And I'll point out that I was far from the first person to do this. There were quite a few studies using Gross-Pitevsky simulations to model neutron star glitches and things. So I'll just sort of lay out setup, which is quite simple. You have a Gross-Pitevsky equation, which is describing the neutron superfluid, and you have a coupling to kind of the container. It's sitting in a trap, which is kind of representing the container of the neutron star or the crust. And you have like a constant electromagnetic spin down, which is what I was saying before. The neutron star is constantly spinning down, or at least an isolated neutron star does. Right, and there's sort of this communication between the crust and the superfluid, which we assume is instantaneous. And in this way, you can kind of self-consistently produce these vortex avalanche events, which correspond to pulsar glitches. So I forgot to say where this is from, but I believe this is from James Douglas's thesis, one of Andrew's previous students. Yes, anyway, so you can plot the angular velocity of the crust, and you can also plot the size of a given vortex avalanche, and you can see that they correspond. Um, and this is in like two-dimensional simulations. And one thing that you see in these types of simulations is that these glitch sizes and corresponding vortex avalanche sizes are distributed as a power law, which is consistent with, for example, pulsars like Crab and their sort of set of glitches. Okay, so yeah, so essentially we're modeling the neutron star interior as just a rotating, decelerating, pinned superfluid. And we can produce these kind of events self-consistently. There are obviously a huge number of caveats as to why this is, very far from the complete picture of a neutron star for a very large number of reasons, and I'm going to touch on a few of those at the end of this discussion. So yeah. Okay. Now, at least, so the two-dimensional simulations were done for a while. One of the things that I wanted to focus on in my work with Andrew was how these vortex avalanches occur in 3 dimensions. So we sort of were motivated by this idea that in principle you can have flux tubes aligned with the magnetic axis of the neutron star, while the neutron vortices are aligned with the rotation axis. Those two axes are misaligned in general, right? So you sort of immediately have this kind of complex 3-dimensional structure, right? Where you have the superfluid vortices can pin to the flux tubes, and they sort of have very different competing alignments, which leads to kind of, the emergence of these complex tangled vortex structures almost immediately. And we wanted to investigate, at least in these toy GPE models, how the vortices move outwards and carry the angular momentum with them, and how they sort of pin and unpin to the flux tubes in these sort of two different cases where you have everything aligned and misalignment between the flux tubes and the vortices. Okay, so that's kind of the broad motivation. So essentially, what I'm going to talk about are these 3 papers, which all focus on the interaction between neutron vortices and proton flux tubes. Okay, so as I was just saying, the flux tubes tend to align along the magnetic axis, while the superfluid vortices will, of course, align in the direction of the angular momentum of the neutron star. You have 3 fluids, of course, but we're ignoring the electrons, which will just be a normal fluid. And we just include sort of the neutrons and the protons, which we think will contribute to, at least to the vortex dynamics entirely. Okay, so the 3 papers first look at equilibrium. So when you don't have any spin down of the neutron star and you're just thinking about the sort of interaction between the vortices and the flux tubes. Then we look at non-equilibrium, we spin down the star. And then there is this paper led by Jackie, which was the much more recent paper from last year, which actually includes the feedback from the protons, because in these 2 works, the flux tubes were just like a static array, and we were just purely looking at the neutron dynamics. Okay, so basically the question we're trying to answer is, how does the interaction with the proton flux tubes impact the sort of dynamics of the neutron vortices, and hence the rotation of the crust, and therefore glitches, which is the things that we can actually observe astrophysically. Okay, so I already sort of mentioned what my setup is. It's essentially just a Gross-Patevsky equation, but you have this interaction term. And in this interaction term, we included kind of a density coupling as well as a current coupling, which is something like entrainment of the 2 fluids. And as I said, we're just using a static flux tube sort of ansatz, which is, obviously an oversimplification, because the proton flux tubes will themselves feed back and interact with the vortices. And this will impact the dynamics, which I'll talk about later. Okay, so this is kind of the model that we use. Okay, so as I already alluded to, you end up with these kind of tangled vortex structures. So in red, I'm showing the neutron vortices, okay? And here the proton flux tube array is exactly at 90 degrees. So it's a little bit of a special case, but you can see the blue are the proton flux tubes, and the vortices are trying to pin to the proton flux tubes while also aligning with the rotation of the neutron star. So you have like this kind of misalignment causes a bit of a frustration because the vortices want to do two things at once. And this impacts the way that they pin and unpin and the way they sort of spin out and carry angular momentum out of the system. Okay, and it's very much not a rectilinear set of set of vortices. So in that sense, it's quite different to a lot of the two-dimensional simulations, which just take this cross section of the trap, and you just have vortices which are essentially just assumed to be perfectly rectilinear. Okay, so that's kind of the equilibrium. What it looks like in equilibrium. But what we care about are, of course, astrophysical observables. And astrophysically, the neutron star is spinning down, and all of this tangled vorticity is kind of pushing outwards and moving through this array of flux tubes. It's pinning to the flux tubes, unpinning to the flux tubes, and it's sort of doing this in this tangled way. So we're going to basically just spin down the star and see how this impacts the rotation of the crust. Because the rotation of the crust is what we actually observe. As the crust of the neutron star rotates, it spins, and that lighthouse beam will sort of pass over the Earth, and that's what we can see. Okay. All right. So immediately there are some very obvious qualitative differences. So here we're looking at the pinned vortex fraction. So when I say the pinned vortex fraction, I mean sort of how much of the vortices are pinned to the flux tubes. So when you have the magnetic and rotation axis perfectly aligned, initially the vortices all pin perfectly to the flux tubes. And as they push out, as the star spins down, they push outwards, and they sort of pin and unpin very spasmodically. Like the entire vortex will pin and unpin from the entire flux tube, of course, because there's no breaking in the symmetry anywhere. If you have a misalignment, this is kind of the structure that you're looking at roughly. So this is sort of, exactly the most, complementary case, which is misaligned by 90 degrees, but you can, of course, have any sort of intermediate misalignment in between. And you start out with the entirety of the vortices cannot be pinned because they can't align perfectly with the flux tubes because they're trying to align with the rotation axis. And also, as they unpin, they do it in a much less spasmodic way because the entire vortex doesn't unpin and pin. It will just be sort of segments of the vorticity. So our argument is, perhaps the vortices will kind of slip past the misaligned flux tubes more easily because they're not unpinning and repinning their entire length. They can just sort of, move around and slip through. And so we're interested in how this impacts the crust and hence glitch kind of events. So that's hopefully what I have next. Yeah, okay. So, okay, well, actually, first of all, we're just looking at, this is the angular momentum of the neutron superfluid, sort of the average angular momentum in time. So this is like perfect alignment. As you can see, it's quite spasmodic, as I mentioned before, as things pin and unpin. If you have misalignment, then the evolution of the angular momentum is much smoother. So you have this very different transport of vorticity to the condensate boundary. Okay, so this is the superfluid, right? But if you remember, the superfluid is kind of coupled to the crust, and that's really what we care about. That's the actual observable. So that's what we're going to look at next. So here we have a few different alignments in red, green, and blue. So you can see the red is when you have everything aligned. So that's like a perfectly rectilinear neutron vortice, right? And you can see that the spin down kind of slows because the vortices aren't moving in these like spasmodic chunks as much. So you have like this kind of retardation of the spin down in the more misaligned case. Um, yes, and this is kind of how the superfluid communicates with the crust. Okay, so now I'm going to get to the most recent work, which again changes the picture slightly. Um, so as I said, in those first two papers, we were talking strictly about like a static flux tube ansatz that was not responding in any way to like the pinning and unpinning events and the vortices moving through the flux tubes. We just sort of imposed this ansatz in the system. Um, but of course, the protons themselves are a quantum fluid. Their vortices will respond. And this is the work led by Jackie, who is a PhD, Jackie Thong, who is a PhD student with Andrew Malatos. And essentially, we sort of used the same code and continued this exploration. But now we solved an equation for the proton superconductor as well. Um, and okay, so here we have kind of the interaction term, which is exactly the same as before, except I'll just point out that we considered only sort of these density couplings. So there was no current couplings. And that isn't because they aren't there, that's just for simplicity. Okay, but otherwise the setup is exactly the same, except this phi, which is the wave function for the protons, is also dynamic and is also evolving as the star spins. I said static flux. Okay, that's wrong. It's not static anymore. Okay. So this is a figure from the paper. Okay, so here you can see now instead of having these perfectly straight aligned flux tubes, you have these wiggly flux tubes that are also dynamically responding to their interaction with the neutron vortices, which are again in red. Okay. So one thing which is different to my first two papers where the fluxes were static is the paired flux tube vortice sort of pinned segments can move together now rather than staying fixed and then unpinning because the flux tubes are fixed. So this sort of changes the picture slightly. Okay. So this is again the dynamics of the crust. But now we're including the feedback from the protons. So actually in this figure, you can see what impact including the feedback does, because we have the different cases. We have including the feedback, including the coupling of the neutrons to the protons and the protons to the neutrons, and assuming they're the same, which is the top. And then we have turning each off, one by one. And then there's just perfect co-rotation in black. Okay, so what it means when you have the vortices moving together with the pinned vortex segments is you get smoother and slower spin down of the crust, and you get smaller rotational glitches. So this is sort of comparing between having no proton feedback and proton feedback. And then the other sort of dimension you can explore is increasing that interaction strength between the neutrons and the protons. And that's what we have here. And you can see as the proton feedback becomes stronger, this sort of slows down the spin down of the crust. Okay, so that's the takeaway from the proton feedback paper. Essentially, as you include more and more complexity into the picture, everything changes slightly. But the overall message is the same, which is that considering the three-dimensional structure and the interaction with the proton flux tubes will impact the way the vortex pinning and unpinning works, and will impact the dynamics of the neutron star's crust. So it's sort of, if you really want a full self-consistent description, microscopic description of the way vortex avalanches work, in principle, you do need to include, an interaction with the proton fluid. Okay, so now this brings me, let me see how I'm going for time. Okay, good. Now this brings me to the caveats for this work, of which there are many. So as I mentioned, the vortices are like 10 femtometers. And of course, the entire neutron star is 10 kilometers. So that's, many orders of magnitude different. So in fact, we expect that there'll be like 10 to the 16 neutron vortices in a neutron star. And there'll be even more flux tubes. So like 10 to the 30. So this is very different to, these little tiny simulations I was just showing you, where we had like around 20 neutron vortices and, at most like 200 flux tubes. This is, just so many orders of magnitude away from the real thing. So this is sort of the primary problem, I would say, with these types of experiments. They're quite interesting for exploring kind of qualitative behavior of these kind of microscopic pinning and unpinning events in the star. Actually mapping that to an astrophysical observable, which applies to like 10 to the 16 of these vortices all at once, is going to be a little bit different. You can have sort of emergent statistical properties of all of these vortices interacting together. So yeah, it's quite a challenge. Yeah, so I would say the takeaway from these types of simulations are sort of purely qualitative in a sense. We're just learning about the vortex pinning and unpinning mechanism, and mapping that into some sort of description of the global behavior of a star requires, extra effort. But there are ways of potentially pursuing this. Okay, so there are a few other things missing as well. So, for example, we were talking about the fact that this is all, singlet S-wave superfluid, but there's also a P-wave superfluid in the star. So once again, this is a totally different story. We have potentially, we expect that there will be these kind of complex vortex structures associated with the anisotropic superfluid, analogous to like helium-3. So this is another complication, which I don't know how thoroughly this has been explored. Actually, I might be behind on the literature. So please let me know if anyone's thought in great detail about, vortex dynamics, including the P-wave effects in a neutron star. The other obvious thing is we're, of course, omitting gravity, which is kind of a huge thing. Like, I think it's not clear that it'll be important at these kind of tiny scales, but in general, a neutron star is a highly, highly relativistic object. So when you're describing like the fluid dynamics of a neutron star, it needs to be done relativistically. Also, the neutron matter is going to be strongly interacting. It's going to be very dense, and the dilute regime doesn't, seem like it would be necessarily the most accurate. Okay, and that's just, that's the tip of the iceberg. There's probably more things you can think of. So this is just to say there are many caveats. So don't take any numbers from these GPE simulations as being like strictly correct in a neutron star context, but really just learn about like the microscopic qualitative picture for the mechanisms of pinning and unpinning. Okay, but this also means there's a lot of work to be done, and there's a lot of room to explore. Yeah, so I think it's quite cool. Okay. Right. So then I just wanted to mention a few little related topics and kind of future directions and prospects. This is just, a tiny, tiny sample of, somewhat recent papers, but there are obviously many more, which I'm not including. So I just wanted to highlight, in terms of this mapping between the macroscopic and microscopic picture, One of the directions that could potentially be pursued here is using like an n-body vortex dynamics picture. So instead of, fully resolving the vortex density and, the core, you can just model the core as like a filament or as a point in like a two-dimensional simulation. Um, and this will, of course, decrease the computational complexity, but it's also going to be very, a lot, very much sufficiently accurate for a neutron star where you have, just a huge number of microscopic vortices. We don't need to resolve the detailed dynamics of, sorry, the detailed structure of the density of the core of the vortex. Okay, so sort of one related work is this work by George Howitt. And these were sort of two-dimensional n-body vortex simulations that he did here. Okay, but there are many works on these sort of n-body vortex simulations that you can look into if you're interested. The other thing I wanted to highlight is there are regions of the neutron star where you expect type 1 superfluidity and other regions where you expect type 2 superfluidity. And there's going to be interesting sort of, behavior where you have the sort of intersection of the two, right? So this is work also by Jackie, who is the lead author of the other paper I was just talking about. Yes, and so he recently published this or posted this. And you can look into that if you're interested in flux tubes and sort of superconductors in neutron stars. Okay, the other work I wanted to mention was this work by Rafa Fuentes and Vanessa Graeber, looking at sort of the detailed post-glitch fluid dynamics and doing like full three-dimensional numerical simulations, which I think hasn't ever been done before, and sort of seeing how this works. Okay, and obviously there are many more. This is just a small taste. Okay. All right. So I think I know you said 40 minutes, but I'm just going to touch on a few last topics, which I think you'll find fun. So hopefully you'll enjoy this. Okay. So I focused on neutron stars, but I really just want to point out that it's not only neutron stars. There are really quantum fluids potentially in many places in the universe beyond our Earth. So one thing which has been particularly kind of hot and exciting recently is this idea of boson dark matter. So that's what I'm going to talk about very briefly. And I'll just say I haven't done any work on this. This is just something I'm interested in and potentially would like to work on in the future. But yeah, so if you have elementary bosons that exist in the universe, potentially like ultralight bosons, these self-gravitating clouds of these bosons can exist in like macroscopic quantum states, and these could be potential dark matter candidates. And they would sort of potentially take a few different forms and be seen in a few different ways if they exist. So potentially you could imagine having a Bose-Einstein condensed cold dark matter halo, like sitting around galaxies. So this would be, very large scales, like a very, very large condensate, of course. And yeah, I put sort of one example here of a reference you can look at. This purple line here is kind of the boundary between Newtonian and general relativistic gravity. So this is a self-gravitating cloud, but it has purely Newtonian gravity. So you just couple with Newtonian gravity through this term here. Yeah, okay. So that's one thing you can imagine. You could also imagine that these could form clouds around black holes. And in this case, you need to, obviously solve Einstein's equations. It's going to be a highly relativistic system. And you'll have sort of this Einstein-Klein-Gordon system if you have a scalar boson. So that's super fun. And then potentially these guys, as the black hole rotates, will emit continuous gravitational waves, which can be detected. And there's a paper here by Max EC about, how to detect these types of systems with LIGO. The other thing you can have is just like an actual star, like a boson star, just consisting purely of these elementary bosons. That's like collapsed. Um, and these stars could potentially exist in a binary, and then that could also emit gravitational waves. So there's a nice paper here by Neil Simonson and William East, if you're interested in that. But there's many papers on boson stars if if you want to look into it. And there are just a few little pictures I wanted to show you because they're so cool. So this is from the paper that I just mentioned from last year. So this is a binary system of boson stars. And they're initially non-rotating, but they have orbital angular momentum. And you can see the vortices form and play a key role. They're very much macroscopic, play a key role in kind of the binary dynamics of these two stars. So it's very cool. The other case I wanted to show you was if you have the two stars are rotating, they'll sort of initially have vortices and merge, and you can see like you can keep track of the vortices by looking at the phase here. So that's really fun, I think. And again, this is not work that I've done. I just think it's kind of amazing how relevant quantum fluids are to these types of systems. Okay, so the very final thing I wanted to mention, which is also super cool, are like these black hole analogs in the lab. So many of you are probably familiar with this paper or maybe even worked on it. So this is a paper by many folks at Nottingham from Nature. But essentially, you have, instead of a singly quantized helium-4 vortex, you have thousands of quanta of circulation. And this, as you know, a black hole has a singularity. So it has this very extreme density gradient going into the singularity. So you need this kind of extreme amount of quantum circulation in order to kind of produce an analogy with a black hole. So essentially, this is going to be something like the gravity well of a Kerr black hole that's rotating. And you can produce this in the lab in this beautiful paper. Okay, and that's really all I had to say. I hope I convinced you that quantum fluids in astrophysics is really fun. I know many of you already work on related topics. But yeah, for those who this is new to, you can see that a lot of the work that you do in quantum fluids has direct relevance to astrophysical systems. And a lot of progress that's being made in terrestrial labs can be sort of directly connected to systems in space. So yeah, that's all I had to say. Thanks so much for listening, and thanks for inviting me once again.
All right, thank you very much for a really nice presentation. Do we have any questions? Please just raise your hand in the audience if you have a question. Well, while we wait for questions, I have plenty of them. I was going to ask you, how do the crust and the core exchange momentum? So you have potentially quantum condensates in both of them, and then for one to feel the effect of the other one, there needs to be some interaction between them.
That's exactly right. Yeah. So sort of the conventional picture is that you have pinning sites in the crust. So in this sort of foundational work by Andrew Balatos and others, well, I guess I don't have, yeah, okay. I guess I don't have a picture of, yeah. But in this sort of, in these descriptions, what you can do is you can have just like a set of nuclear lattice pinning sites. So this amounts to just imposing like a structure onto your trap, at least in the GPE simulations. But in actual physics, what these represent are in the crust of a neutron star, you have these, this regular nuclear lattice, and there's like an energy minimum as the vortices in like the crust of the star pin to the in the inner crust pinned to these sites. In the outer core, the picture is more like the flux tubes are coupled to the crust, and the neutron stars can pin to the flux tubes. So there's sort of different regimes and different parts of the star, but sort of the underlying mechanism is the same, which is that you have these pinning sites, which are rotating with the crust that the neutron vortices pin to. But it's quite complex, and I would say not fully understood, at least not by me, maybe by others. But yeah, that's kind of the broad picture. Yeah.
Well, I mean, the reason I'm asking this is that if you have just let's say two different phases of, well, my case would be helium-3
Yeah.
superfluid, then often the interactions with not just container walls, but also between the two phases are hindered and only take place after some sort of deformation or critical velocity or something like this between the two systems.
Totally. So I mean, yeah, go ahead.
No. There is a question, but just let's finish this one first.
Yeah, I mean, so in this GPE model, we're assuming that there's like this instantaneous coupling between an interaction between the superfluid and the crust. But this is not strictly accurate. Like there's going to be some process by which this occurs, which has some time delay.
Okay. Well, now we have plenty of questions. So I think Heide is the first one. Please just unmute and go for it.
Thank you. So thanks, Lisa, for the talk. I just wanted to ask, I mean, the systems that you're describing are very complicated, and there's a lot of physical effects, and one needs to make approximations. And you've mentioned at least three things that I don't think they're included in the models you've looked at so far, which is P-wave superfluidity, the electron fluid, gravitational effects. And I guess in any form of modeling, one needs to decide what to prioritize and what is most important. So I didn't quite get a sense of, if one wants to go to the next level of complexity, what is most important?
I think the most important thing would be to include more vortices. Like even to just see like the self-consistent emergence of vortex avalanches through self-organized criticality, you need a certain number of vortices in your system. So this has been explored with like two-dimensional condensates, but it really hasn't been explored how the vortex avalanches really cause spin up events that look like real pulsar glitches in like full three-dimensional simulations with a proton superfluid, at least not to my knowledge. So I think that would be the very first thing to understand. Things like gravity, I think even just including Newtonian gravity, I think this has been already done actually in these kind of GPE simulations. That's quite interesting. But I think, so to answer your question, there are obviously many interesting directions to explore, but definitely the key problem with these simulations is the scale. Like definitely the biggest problem, I would say.
So you don't think that, for example, the type of vortex dynamics that you would get or vortex interactions that you would get from a P-wave superfluid would be significantly important compared to this just scaling up of the number?
Okay, if we're just talking about like the actual sort of microscopic mechanisms, I think it could make a large difference. But it sort of depends which part of the neutron star you're talking about. So maybe if I can go up again. As you probably know, the P wave is kind of dominant in the inner crust of the star. And this is often where people talk about glitches, because you just have like this neutron superfluid and you have this interaction with the pinning sites in the crust. But this is going to be P wave as far as I'm concerned. So the S wave in the core is probably pretty reasonable because it's definitely the dominant superfluid, at least to my knowledge. So it sort of depends which part of the neutron star you're modeling. But I think definitely looking at P wave for the crust, I think could change some of these mechanisms, and it would be quite interesting. It would be maybe challenging, but I think it would be important actually. Yeah.
All right. Gabriel is the next one.
Thank you. Thank you for talk. Um, I have actually two questions. And the first one is, so you already mentioned that there is a pinning in the core and pinning in the crust. So do you have any suggestions on how to determine which pinning mechanism is the dominant one from the perspective of the glitch
Ooh.
phenomena?
I do not know. I do not know the answer to that. Um, Perhaps there are other people in the audience who have a better idea. Um, yeah, I don't know. Um,
Okay.
sorry.
So the second question, how do you fix parameters or coupling constants in your model to mimic the nuclear
Yeah.
matter?
So that's that they're completely free parameters. So we just explore a range. Yeah, but this is again another actual interesting thing to explore, which would be choosing the coupling parameters so that they're self-consistent in some sense with neutron matter would be another step. But yeah, in this case, they're completely free parameters. We just explore a range of different density couplings and current couplings and see how this impacts the simulation. But in principle, these parameters will have a value, which should be selected based on nuclear physics. Yeah, absolutely.
Thank you.
All right, Magnus.
Right, thanks. Thanks for a lovely talk. I want to go back to, you mentioned briefly the P-wave superfluid. I know that wasn't the main thrust of your talk, as
No.
so to say, but you mentioned the core structures and analogs with
Yeah.
helium-3 and so on. And of course, we know quite a lot about different core structures, both from helium-3 and also from
Yeah.
spin Einstein condensates, where you have all of this fantastic topology, and we've done a lot of things just for the pure interest. But from
Totally.
your point of view, trying to understand the neutron star, what is the interesting question about the core structures that you want that is important to you from the astrophysical perspective?
I mean, honestly, I don't know, but I mean, I think like something like this, like if you have a vortex sheet as opposed to like a set of vortex filaments, I think, just qualitatively, just from intuition, it seems like immediately that would lead to qualitative differences in kind of the pinning behavior. So I think, at least from my naive perspective, doing like numerical experiments in a similar fashion with like sort of my work with the coupling to the proton flux tubes and just exploring how the pinning and unpinning events change and how the coupling to the crust will change if you have these kind of much more exotic vortex structures. I don't know. That's really all I had to say about this. I'm not an expert in P-wave superfluids. Many of you will know far more and maybe have a lot of interesting ideas. But I just wanted to touch on it because I think there are so many cool parts of like our understanding of quantum fluids which are applicable to neutron stars. I think already, and I don't know how thoroughly they've been explored. But I apologize if there has been work on um, you know vortex dynamics, P-wave superfluids in neutron stars. Please let me know if that's the case because I'd be very interested. Yeah. But that's
Right,
that's really all I was
no,
saying. Yeah.
that's fine. I'm just interested to hear
Yeah.
sort of what questions are being asked from that side, because I know the spinor BCs, but I don't know the neutron stars.
Yeah. Yeah. I mean, it's just really if the vortices look different, they're going to interact with the pinning sites differently. I think, and that's going to affect the crust of the neutron star. That's going to change the glitch observables. Yeah.
Right, lovely. Thank you.
All right, I don't at the moment see any other questions. I'll take this moment and remind you that if you'd like to be added to the mailing list where we remind you about this the webinars in this series, then just send me an email or put something in the chat in this meeting, and that can be sorted out. Most of my questions in the list here have already been answered or asked by other people, but there was one which I still wanted to ask, which is would there be some consequences anticipated from phase transitions in the superfluids, let's say in the core between the different pairing states, or well maybe other phases? At least in a triplet system, you can have multiple different phases.
This is not something I've thought about at all. I would imagine yes. I would imagine yes, but yeah, I'm sorry. This is not something I've thought about. But yeah, I would think so. Um,
Well, in lab experiments, there are all sorts of consequences. So that's why I was
exactly,
asking. Yes.
exactly. I mean, there's yeah, it's really okay. It's not just a giant terrestrial condensate, but I think the analogies qualitatively seem to work quite well. Um, Obviously, this is another thing which we're sort of ignoring is that this is extremely dense nuclear matter. There are only certain regions in the neutron star where um, you know really the terrestrial experiments are directly applicable, but at least in those regions I think you would expect to see the same kind of consequences,
All right.
but not something I've thought about too much.
Sure. Well, as I don't see any other questions, then I think we are nicely within the hour still, and
Perfect.
it's a good time to slowly wrap up. So thank you very much for this very interesting presentation. It's nice and clear. And this, as usual, will go on YouTube. So if you want to return to these things, then that's the way to do it. And there will be at least one more neutron star talk in this series by Vanessa, who I believe is in the audience. That's in January. Whether or not we have more talks between now and then is still a matter of discussions between potential speakers. So we'll inform you by email and on our website. And with that, well, thank you to everybody who joined us today, in particular, Lisa, for giving the talk.
Thank you so much. It was a pleasure.
Good. Okay, and I will close the meeting now.
Bye.
Thank you. Bye bye.